Hello and welcome back to this STM32 Beginners Guide series. In today's episode, we're going to explore analog to digital conversion, also known as ADC. I'm going to show you how to read ADC values from a potentiometer and how to use those values to control the brightness of an LED. By the end of this episode, you'll be able to read any analog input signal using your STM32 microcontroller, and you'll be able to use those ADC values to drive any digital output. My name is Ali and you are watching CGHQ. What is ADC and how does it work? ADC stands for analog to digital conversion. It's a process that converts an analog signal, which can have any value within a specified range, into a digital signal that has discrete steps. This is crucial when working with sensors or inputs like potentiometers, which output analog voltages that need to be read by a microcontroller. How an ADC works is that it takes samples of the input analog signal at regular intervals. This is called sampling. Each sampled value is then mapped to the nearest digital level. The number of levels is determined by the ADC's resolution. This process is called quantization. The resolution of an ADC defines how many discrete levels the ADC can output. For example, a 12-bit ADC such as the one in the STM32 A41RE can output 2 to the exponent of 12 or 4096 discrete values. To read ADC values, we'll use a simple circuit with a potentiometer connected to one of the ADC pins on the STM32 A41RE. You need to connect the VCC and the ground terminals of the potentiometer to 3.3 volts and one of the grounds in the STM32 microcontroller. Then connect the signal terminal or the middle leg of the potentiometer to pin A0, also known as PA0 in the STM32. Let's start writing code. Go ahead and open STM32 Cube IDE and create a new STM32 project. Go to where it says board selector and search the STM32 microcontroller that you have. Click on next. Click on next again, and then here where it says project name, we're just going to call our project ADC and we're going to save it in the default location. Then we're going to click finish. The pin that we're using to read our ADC values is pin PA0. So you have to come here to PA0, click on it, and then select ADC1 in 0. When this is done, you can come here to analog, click on ADC, and you can see that channel 0 of our ADC1 has been selected and it is now active. You don't really need to change any of these values here. You just need to come here to continuous conversion, and then we're gonna enable continuous conversion. Then you can either click on Control and S, or go to file and select save. Do you want to generate code? Yes. And do you want to switch perspectives? Click on yes. Here where it says user code begin to, we're just gonna declare a variable that we're gonna use to store the ADC values that we're going to read. So I'm just gonna say u int 16 underscore t, and then I'm gonna call the variable read value. The first thing we're going to do is that we're going to start the ADC. So we're going to type HAL underscore ADC underscore start. Then we can hold control and click space for auto completion. And we see there's 3 ways we can start our ADC. We can start it in the normal mode, or we can start it with direct memory access, or we can start it using an interrupt. For this video, we're just going to use the normal one, and then double click on ADC1 and add a semicolon. The next thing we're going to do is that we're going to type HAL underscore ADC underscore poll. We're going to poll for conversion. So hold control and click on space and double click on this one that says ADC poll for conversion. Double click on ADC1, and then for the timeout, we're just going to type HAL underscore maximum delay. We need to take the variable that we created and then capture the ADC values and store them in this variable. So we're going to type read value is equals to HAL underscore ADC underscore get, and then hold on control and space for auto completion. We're going to double click on this one that says ADC get value, and then ADC1. Now that we have captured the ADC value and stored it inside of the variable that we created, we need to display these values so that we can see the kind of values that we are working with. To do this, we're going to use serial communication, specifically UART. So we're going to be sending these values to a console to be printed out using UART. I'm not going to get in deep into details with UART because I already have a video that I made that covers UART in detail. Please check the video out. It's also in this STM32 Beginners Guide tutorial series playlist, but I will leave a link to the video in the description section below. To add UART, we need to go back to the graphical initialization tool, and then here where it says connectivity, we're gonna come to UART and we're going to initialize UART2. So click on UART2, and then here where it says mode, select asynchronous. Another thing to take note of is the baud rate. Then click on control and save, generate code, and switch to the new perspective. Now that UART has been initialized, we need to create a buffer for the data that is going to be transmitted. So we can say character, we can call the buffer tx_buffer. Now that the buffer has been created, we're going to take the ADC value that we have read and we're going to insert it inside of the buffer so that we can transmit it to a console via serial communication. We're going to say sprintf, and then we're going to say tx_buffer, and then in quotation marks we're going to say the percentage symbol HU. Then we're going to add a carriage return and a new line. I'm going to add a comma and then say read value. And then to transmit this information to the serial communication console, we need to say HAL_UART_transmit, and then hold on control and space for auto completion. Then we're going to select UART2. Here where it says pdata, I'm just going to type open bracket uint 8_t and then asterisk. Next to this, I'm going to write tx_buffer. Then here where it says size, I'm going to say string length of the tx_buffer. And then for timeout, we're just going to say HAL_max delay. Here I'm going to add a small 10 millisecond delay. Then we're going to scroll up to here where it says user code begin include. Then we're going to add two header files. The first one is #include string, since we're using strings, and then the second one is going to be #include stdio.h. When this is done, we can connect our microcontroller to our computer and then come here to this icon to build our project to see that there are no errors, and then it says finished with 0 errors and 0 warnings. We can then come to this green play button that says run and then click on OK to upload the code to our microcontroller. When this is done, you need to open a serial communication software like Party or Termite, and then make sure that the COM port that is labeled here matches the COM port of the microcontroller that you're using, and then also make sure that the speed here matches the baud rate that we selected when we were initializing UART. And then we're going to click on open, and as you can see right now, we are reading values from our potentiometer. Right now the potentiometer has been turned all the way to its maximum value, so you can see that when I twist the knob on the potentiometer, the values that we read with the ADC keep changing, and they range between 0 and 4095. Since we are now able to read ADC values from the potentiometer, we're going to use these values to control the brightness of an LED by mapping the ADC values to the duty cycle range of one of the PWM pins on the STM32. To do this, you need to connect an LED to pin PA5 labeled as D13 on the STM32 F41RE and the other leg of the LED to ground through a resistor. We need to go back to the graphical initialization tool and we need to initialize PWM on one of the pins in our STM32 microcontroller. We are using pin PA5, so you need to come here to PA5 and click on timer 2 channel 1, and then you need to come to timers and then click on timer 2. Then here where it says channel 1, you need to click on it and go to PWM generation channel 1. I already made a video going through PWM and how timers work to generate PWM signals. Please also check out that video. It's also part of this playlist labeled STM32 Beginners Guide series. I will also leave a link to that video in the description below. For our prescale, we're just going to use the values we used in the previous PWM video. So I'm just going to type 19 here, and then here at the counter period I'm going to type 209, and then when we scroll down here where it says PWM fast mode, I'm just going to enable fast mode PWM. Then we're going to click on Ctrl S. We need to come here and start the timer for PWM generation. So we're going to type HAL underscore team underscore PWM and then hold on control and space for auto completion. Timer 2 channel 1. So here we're gonna say team underscore channel control space and then double click on channel 1. When this is done, we need to map the ADC value to a variable that will control the duty cycle of our PWM signal. So the idea is that when we turn the knob on our potentiometer going from left to right, going from the low value to the maximum value, we should see the brightness of the LED increasing and decreasing as well. So I'm just going to type STM32 underscore T and I'm going to say PWM value is equals to red value multiplied by 209 divided by the maximum, which is 2 to the exponent of 12, which is 4095, because we start counting from 0. After mapping the ADC value to this PWM value variable, we need to insert this variable into the compare register so that we can control the duty cycle of our PWM signal with the ADC values. So I'm just going to type underscore underscore HAL underscore team underscore set underscore compare and then control space, and I'm gonna come up and copy these two, paste them inside, and the last one is going to be this variable that we created. Paste it here as well. We're then going to build the project to check if there are no errors. So now we're going to upload the code to our microcontroller. And as you can see, when I turn the knob in the potentiometer, you can see the brightness of the LED increasing and decreasing. In this episode, we explored ADC and how to use it to read analog signals with the STM32. We also learned how to use those readings to control the brightness of an LED via PWM, as well as how to print ADC values for real-time monitoring. Please check out the next video in this series where I will show you how to do serial communication via USART. If you found the video helpful, please like, share, and subscribe. And if you have any questions or any feedback, please leave them in the comment section below. See you in the next episode.